Alright, so this video is the third part of a series on knight endgames and better understanding the knight in general. In the first video, I explained why king and two knights versus king is a drawn endgame, and then in the second video, I went over some seemingly paradoxical cases where a king and just one knight are sufficient mating material. In this video, I'll be clarifying a lot of the raw mathematical properties of the knight, which is a very neglected subject. So this video is going to have a lot of math in it. I'll be demonstrating how a lot of different math and chess concepts are related to each other and can be easier to understand when studied together. So first, let's establish a more mathematical way of classifying the pieces. There are two main types of movements in chess. There are leaps and then there are also rides. A leap is a single movement in which a piece leaps from one square to another, disregarding any obstructions in between. And a ride is a repeated leap in the same direction through unoccupied squares. So, a wazir is like the leaper counterpart of a rook, and a furs is like the leaper counterpart of a bishop. The king's movements are a combination of the furs and wazir. You can also have combinations of different leaping and riding movements together. The Knightrider would be the rider version of the knight. It's like a knight that can pin and skewer things. It can be a little confusing, so I'll show a tactical example. This position would be checkmate if the Knightrider on g5 could leap in a path of 6-3, but since it's a 2-1 rider and not a 6-3 leaper, there's an obstruction created by the white king on c7, so white wants to play king to c8 checkmate, but black's Knightrider on g6 controls c8, though the board's too small to maintain it since white controls e7, so black's in zugzwang, and with white to move, the Knightrider on g5 could just waste a move on e6, something that a traditional knight can't do. So, black's best move would be Knightrider to e7, avoiding immediate checkmate, but white simply takes and then proceeds to mate with two Knightriders. And checkmates with two pieces were something I talked about in the first video, where I broke down some of the concrete abilities required to accomplish a checkmate, which clarified why king, knight, and bishop versus king can only checkmate in a corner that's the same color as the bishop, and why king and two knights versus king is a draw. But two Knightriders are able to accomplish the corner mate pattern because a Knightrider has the ability to transfer control of the third square from the corner to the corner square, much like a bishop. So even a Knightrider plus a regular knight would be able to force checkmate. In fact, a Knightrider plus almost any piece can force checkmate if the piece controls a square adjacent to a corner. Next, I'll show a 63-move checkmate involving a king, Knightrider, and 3-rider versus a king. A 3-rider moves like a rook, but leaps 3 squares at a time instead of 1, so 9 of them are needed in order for every square on the chessboard to be within range of a 3-rider. We'll get to the concept of color boundness in just a bit. So, the 3-rider is a really weak piece, but if its color complex lies adjacently to one of the corners, then it's just strong enough to assist a Knightrider in forcing checkmate. A 3-leaper wouldn't be strong enough unless the defender's king was already near a mating corner. So although checkmate can't be forced in the h1 corner, black can use checkmate as a tactic to force white away from the wrong h1 corner. So now white avoids the h8 and a1 corners, which are checkmating corners, and ends up in the safe a8 corner, but since the 3-rider controls valuable squares on the b file, black can set up barriers to prevent white from returning to the safer h1 corner. So now we reach the final stage of the endgame where white is mated in the a1 corner. Black uses the corner mate pattern as explained earlier and in the first video. So, learning about color boundness can help to better understand the concept of opposition, which is one of the building blocks of endgame theory. A piece's color boundness is the number of colors or unique markings required to illustrate its potential range on a chessboard. For example, the color boundness of a bishop is 2, because you need 2 colors to illustrate both possible ranges or realities for a bishop. The dark squared bishop exists in a reality completely separate from the light squared bishop. In other words, it's physically impossible for them to be in the same range as each other. Ironically, a king and 1 dark squared bishop win against a king and 32 light squared bishops on the standard 8x8 chessboard. The color boundness of a 3-rider is 9 because you need 9 3-riders in order for every square on an infinite board to be within range of a 3-rider. So here there are 9 different shades of color to illustrate the separate realities for the 9 possible 3-riders. Here the upside down rooks represent 3 leapers which have the same color boundness as their rider counterparts. Notice how each one stays on its color when it moves. Each 3-leaper can make a 3x3 square which has an area of 9, and the 9 colors illustrate that equality. A 2-leaper has a color boundness of 4, since 2 squared is 4. Understanding the 2-leaper can make it simpler to understand many of the concepts of king and pawn endgames, because the concept of opposition requires breaking up the board into 4 regions, identical to the realities of 2-leapers. So here the board is divided into 4 colors as a way to better understand this concept. A 2-leaping distance is the closest that 2 kings can possibly be to each other, and whichever king is forced to move is going to give the other king more choices than its counterpart. Whether or not this is important depends on the specifics of the endgame. If kings are in the same 2-leaper reality, then the king who has to move is the less powerful king, but if kings are not in the same 2-leaper reality, then the king who has to move is the more powerful king, by moving into the same 2-leaper reality. Being the more powerful king is called having the opposition. It can be used defensively to prevent the enemy king from invading, or offensively to invade where the enemy king leaves undefended. So with black to move, black can't forcibly access any of the squares marked with X's, because white has opposition and can choose to use it defensively by mirroring black's moves. The 9th rank is sort of like a mirror here. But white can also use the opposition offensively to cross the 9th rank into black's territory. Black's king can only maintain defense of at most 2 files, so white can choose any region of squares that consists of at least 3 files and plan to forcibly access at least one of those squares. But of course other things on the board are going to interfere with the raw concepts of king versus king, so let's look at an example of applied opposition. So here's a position where the key squares are e5, e6, and e7. If black can keep white's king off these squares, then black should be able to safely defend this position, since white's pawns aren't advanced enough for any breakthrough tactics. Whether or not black can keep white's king off e7, e6, or e5 depends on who has the opposition. If it's white to move here, the position is a draw. After king to g5, king to c5 maintains the opposition. White can try king to g4, trying to exploit the fact that the d3 pawn controls c4, stopping black from keeping the opposition. But black has a pawn too, so after king to d4, white can't keep the opposition with king to f4. White has no choice but king to f5, and white wins if a pawn trade occurs, so black simply regains the opposition with king to d5, resulting in a similar situation we started with. If king to g6, then black's only drawing move is to transpose back to the starting position with king to c6. Even though it's often a good idea to get opposition from as close as possible, here it would run into the obstruction created by the e5 pawn. Someone with concrete knowledge of oppositional concepts wouldn't blunder a position like this for black, but without knowledge of these concepts, it's not that hard for somebody to mess up. So here, black is forced to give up control of one of the key squares. Now the pawn once again stops black from gaining opposition and forces black to give up more territory. Now there's no way for black to maintain defense of the pawn, so a pawn trade occurs and white ends up with a winning king and pawn versus king endgame. If it's black to move in the starting position, then white wins by force without needing to get lucky. So black to move is forced to step away from one of the key squares, then white comes closer in the opposite direction, exploiting the fact that black can't both seize opposition and maintain control of key squares. Black has to defend key squares, then white regains opposition from a closer distance than before. This process is called outflanking, and it's easy to understand this process if you study it on a larger scale. So let's say it was white to move here, and black was trying to access a8 or c8. Black's method of reaching a key square would be to keep opposition until both kings are on the b file, then break opposition and come closer. It would be wrong to break opposition with the kings on the C file, because then white can seize opposition without allowing black to access either key square. But by choosing the file between the key squares as the correct place to break opposition, white can't seize opposition without allowing black to access a key square. Seizing the opposition with king to C4 here would prevent black from accessing C8, but not A8. So white would be forced to return to the B file and allow black to regain opposition at a closer distance from the key squares. Black can repeat this process as necessary. So that was an example of applied opposition. Next we're going to look at how to calculate the color boundness of any leaper, rider, or combination piece, and it actually turns out to provide some very intuitive methods of understanding trigonometry. So we'll start with what I call rhombus leapers. They're leapers with 4 moving choices who are able to outline a rhombus or square by moving 4 times, using each ability once, and returning to its original location. The color boundness of a rhombus leaper is always equal to the area of the rhombus it can create. The color boundness of any x leaper is x squared, and the color boundness of any xx leaper is 2x squared. In other words, it's double the color boundness of its corresponding x leaper. So it's very simple to calculate the color boundness of x0 leapers and xx leapers because their 2 pairs of moving paths correspond to a normal xy coordinate system. They're all based on the 1 leaper, so their concept shouldn't be any more complicated than the 1 leaper, also known as the Wazir or unit vector. Leapers of the form xy, where x and y are not equal to 0 or equal to each other, are much more complicated because they have 8 moving choices. They aren't rhombus pieces. When a piece has more than 2 pairs of moving paths but only spans out a 2-dimensional range, its paths are going to overlap onto each other, unlike in a simple xy coordinate system. A piece with 3 pairs of moving paths, which we can call a hexagon piece, is going to correspond to an xyz coordinate system, where its overlaps on the 2D board correspond to viewing a 3D object from a 2D perspective. And a piece with 4 pairs of moving paths, such as the knight, which we can call an octagon leaper, is going to correspond to a 4-dimensional coordinate system where its overlaps on the 2D board correspond to viewing a 4D object from a 2D perspective. When you break up a knight's moves into just 2 pairs of moving vectors instead of 4, there aren't any overlaps, so it's just a rhombus piece with an easily calculable color boundness. There are 3 different rhombuses you can draw using knight moves. One has an area of 3, one has an area of 4, and one has an area of 5. You can classify the 3 types of rhombus knights as diagonal rhombus knight, rank and file rhombus knight, and square rhombus knight. There's 1 type of hexagon knight, there's 1 type of octagon knight, the normal chess knight. 3 rhombus knights, 3, 4, and 5, have a special correspondence to a right triangle with side lengths of 3, 4, and 5. The angles of the 3 types of rhombus knights will correspond to the angles of this triangle. This is a very intuitive way to understand many trigonometric identities. Before we get into those, first let's establish how to find the areas of rhombus pieces and prove the Pythagorean theorem. You can prove the Pythagorean theorem with just some algebraic manipulation of a square rhombus. This also shows how to find the color boundness of a square rhombus piece. The rank and file rhombus and the square rhombus have pretty intuitive areas, since you can just take the area of the rectangular region occupied and then subtract the triangles it doesn't occupy. With a diagonal rhombus, you have to subtract 2 additional squares, but it's still pretty intuitive. If you square the area of the rank and file rhombus and add it to the square of the area of the diagonal rhombus, then you get the square of the area of the square rhombus. This is how to verify that the 3 rhombus leapers of any xy octagon leaper are going to correspond to a Pythagorean triple. When you fit each trio of rhombuses together, they make hexagons, which are 2D projections of cubes. So these model the movements of hexagon pieces, but since the movements behave 3-dimensionally on a 2-dimensional board, we can't calculate the color boundness simply by finding an area, and we can't do it by finding a volume either, since these aren't actually 3D shapes. It turns out that the color boundness of any xy hexagon or xy octagon leaper is going to be the greatest common divisor, or GCD, of the color boundnesses of its 3 rhombus areas. but you only need to find the GCD of 2.
This table lists the color boundnesses of different XY leapers. The red numbers are the color boundnesses of the hexagon and octagon pieces, and the 3 columns of numbers to the right are the color boundnesses of the rhombus pieces, which are Pythagorean triples. The Pythagorean triples with a GCD of 1 are what we call primitive Pythagorean triples. Notice how each piece with a color boundness greater than 1 is based on a more primitive version of that piece. So, the camel is like a twin of the knight, because if you only acknowledge the squares in the camel's reality, then the camel's moves are essentially identical to the knight's moves. Notice how the angles of a diagonal rhombus camel are the same as in a rank file rhombus knight, and vice versa. You could say that knight times furs equals camel. A furs leaps at a distance of the square root of 2, and a knight leaps at the distance of the square root of 5. And when you multiply those together, you get the square root of 10, which is a camel's leap. The camel's movements are also 45-degree rotations of a knight's moves. So you could say that a knight angle plus a furs angle equals a camel's angle. So we have 2 intuitive equations: knight times furs equals camel, and knight angle plus furs angle equals camel angle. This suggests that there's a correspondence between adding angles together and multiplying lines together, and understanding this correspondence can make trigonometric identities a lot more intuitive. But first, let's let all that sink in and go back to establishing how we know that the color boundness formula works.
There are various different ways of computing color boundness, but they all involve the concept of greatest common divisor, which is like a one-dimensional version of color boundness.
It has to do with the Euclidean algorithm, which is an iterative process for finding the GCD of any 2 numbers. We need to show that the Euclidean algorithm is simply a one-dimensional version of computing color boundness, and that computing 2-dimensional color boundness is simply a 2D version of the Euclidean algorithm. So first, let's think about how we would find a piece's color boundness manually. So we know a knight's color boundness is 1 because a knight can travel a distance of 1, so we can use 1 leaper movements to map out the rest of a knight's reality. And we know a camel's color boundness is 2 because a camel can travel a distance of 1-1 but not 1-0, so we can use 1-1 leaper movements to map out the rest of a camel's reality. So basically what we're doing is moving a piece around manually and trying to get it as close as possible to its origin without actually returning to its origin. When we find the closest possible x0 or xx distance to the origin, we simply take the color boundness of that leaper. So we're simply converting an xy leaper into a square leaper with the same color boundness, thereby making the color boundness easier to calculate. The Euclidean algorithm is easy to understand by thinking of the one-dimensional number system as a one-dimensional chessboard, where counting by 2s is like moving a 2-leaper, where even and odd numbers represent the 2 possible realities of a one-dimensional 2-leaper. And counting by 3s is like moving a 3-leaper, etc., etc. The color boundness of an x-leaper in d dimensions is x to the d. When dealing with pieces with more than one choice of movement length, their paths are going to behave more than one-dimensionally, so we can solve this problem the same way we did when working with xy leapers in 2 dimensions. Just try to get as close as possible to 0, and then take the color boundness of a piece with that single type of moving choice. This is the equivalent of applying the Euclidean algorithm. The color boundness of any one-dimensional chess piece is going to be the GCD of all its moving choices. Studying the ways that numbers behave in base 10 can help better understand GCD and Euclidean algorithm, since you probably already have an intuitive idea of how counting in base 10 works. The GCD of 10 in any number will always be the same as the GCD of 10 and the last digit of that number. If 2 numbers a and b have a common divisor c, then adding or subtracting any amount of a's and b's will always result in a number that has c as a divisor. So finding the greatest common divisor of 2 numbers a and b is equivalent to finding the smallest possible positive number that you can reach by adding or subtracting any amount of a's and b's. Once we can't go any smaller, we'll know that there aren't any common divisors larger, since no amount of adding or subtracting will ever yield a result without c as a divisor, and a number can't have a divisor larger than itself. So, this is the Euclidean algorithm for finding the GCD of 2 numbers. We start with 2 numbers a and b, where b is the larger, and then keep subtracting a's from b until we reach a new number r and can't subtract anymore without going under 0. And if our new number r equals 0, then we know our GCD is A. Otherwise, we'll let this new number R replace A and our old A replace B. Then we repeat the algorithm using our new values for A and B.
So when taking the GCD of 33 and 84, notice how every number involved in the algorithm is a multiple of 3. And since 3 is the smallest possible positive number we can yield, we know it's our answer. Notice how if we divide all these numbers by 3, we get the Euclidean algorithm for finding the GCD of 11 and 28, which is 1. So any pair of numbers whose GCD is not 1 is going to have a corresponding pair whose GCD is 1. This is equivalent to fraction simplification. So in order to have a more universal understanding of why the Euclidean algorithm works, we can create an every fraction tree.
We can use this knowledge to construct an every fraction tree, which consists of all possible rational numbers in existence, excluding whole numbers and improper fractions. We generate this tree by starting with 1/2, then we add 1 and 2 together, and we know this new number 3 is co-prime with both 1 and 2. Therefore, we know of two new rational numbers, 1/3 and 2/3, and we can repeat this algorithm knowing that the sum of each co-prime pair will also be co-prime to both numbers. This results in a very intuitive way to look at all the possible fractions in existence. Now, ironically, I created this same tree in 2011 when studying the ways that hexagonal chess leapers manifest themselves into the square-tiled world. There's a one-to-one correspondence between hexagonal tiling and square tiling, so any XY hexagonal leaper can be described in terms of traditional chess leapers. Each hexagonal leaper can move as two new types of leapers when it transitions into the square-tiled world, and those two new types of leapers represent two new nodes on this every fraction tree. So this tree should actually start with 0/1 representing the rook, and then 1/1 representing the bishop, before we get to 1/2 representing the knight. And then that would be a more accurate way of modeling the steps of the Euclidean algorithm, which always corresponds to starting at some point on the every fraction tree and then climbing to the root starting at 0. The GCD of 33 and 84 is 3, and every step of the algorithm yields multiples of 3. So the ratios of these numbers are the same as if we're finding the GCD of 11 and 28, and then finding the GCD of 33 and 84 would correspond to beginning at the ratio 11/28 and climbing to the ratio 11/17, then climbing to 6/11, then to 5/6, then to 1/5, 1/4, 1/3, 1/2, 1, and finally 0.